Okay, welcome back. Now, last week we spoke about we started speaking about the atmospheric pressure. And one of the jobs that I gave you people to do was to plot a number of things. First of all, I wanted you to plot the pressure against the altitude. So we're going to have a look at how the pressure and altitude affect each other. Okay, that's one. Secondly, we're going to have a look at how the temperature and altitude also correlate with each other. Okay, so one of the things I asked you to do last time was to calculate the temperature that you'd expect to get at various altitudes. Now clearly from the data, from the plotted data, we can see that the altitude, that as starting from here, starting from sea level, around about 101 kilopascals, all the way down, so we're climbing now, climbing in the altitude, but you can see that the pressure is dropping. By the time we reach 30,000 meters, which is just about on 100,000 feet, so 30,000 meters, you see that the pressure in kilopascals has practically fallen to almost zero. Okay, so in other words, as we go higher up from sea level over here, and we go higher and higher and higher and higher, by the time we reach 30,000 meters, so roughly 100,000 feet, we find that the pressure has fallen away to practically nothing. Just 1 second and I'll get you your sheet, okay?
I'm taking it back now.
Oh, you're taking it to it. Okay. All right. Thank you. Thank you for doing that.
That's all right.
Okay.
Thank you.
And I'll give you the other graph. Okay. See me afterwards, and I'll give you a copy for her as well. All right?
All right.
Of the two graphs.
Okay.
Okay. Okay, all right. All right, so this is a clear indication that the higher up you go, the less and less and less is the pressure. There's no doubt about this. This is measured in with instrumentation, with barometers and high-level balloons that go up, as well as weather rockets and the like. Okay, so this data, thanks for collecting it, is based on experimentation. Now, we also have here a graph that tells us what the altitude, so the altitude compared to the temperature in Kelvin. Now, as you can see over here, looking at the sheet that you have, so look at around about 260, say close to 280, okay, we have zero. That would be 0 degrees C. Okay, so 273 is 0. 273 Kelvin is 0 degrees C. And as you can see, as we get towards the surface, okay, our altitude is 0, then we have an average temperature of around 290, and that's going to be 298. Okay, would make it 93 would make it 298 would be 25 degrees, so around about 20 degrees, okay, over here, okay, where it stops here, okay. All right, now, as you can see, as we get up towards, this is altitude in kilometers, so this is kilometers now. To think about that, so this is 30 kilometers, okay. So this is 30 kilometers. This over here on your graph is 10, 20, 30. So we're looking at round about here. So this point over here is this point over here. Okay, just at about the stratosphere, and you can see from here that it is quite cold, well and truly below zero by the time it gets there, and still below zero, well and truly below zero by the time it gets to 30,000 meters or 30 kilometers. So there is not only a correlation between the pressure and the altitude, but the temperature and the altitude. Now, we know, I'll put these away. We know that PV equals nRT. So if we're keeping the volume constant, if the volume remains constant, then the pressure changes. So if pressure changes, so we have a change in pressure, we have a change in temperature, R is a constant, okay, and V is a constant, then it follows that the number of moles must change. And this change is the moles getting less and less. So number of moles must change, so make sure you get this down. Number of moles gets less and less. Okay, so just to quickly go over that, we have a changing pressure, a change in temperature with altitude. We've got R, the gas constant is a constant, and we're maintaining a constant volume. So we're maintaining a constant, say, cubic meter, and because these are changing, then it follows that if these are constant, these over here, then moles must change. Okay, so the number of moles is changing, the number of moles is getting less and less and less, and this of course accounts for the difference in pressure. Okay, there's less and less stuff. So at the end, we have Earth, and this is highly exaggerated. Atmosphere, as we leave Earth and head up in altitude, the gradient gets the pressure gradient gets less and less and less, and simply at this point, at some point over here, we usually mark that at about 100 kilometers. There are practically no very few gas molecules per cubic meter at this stage. So it starts off being quite high and ends up being practically none. But now we know, if we, for instance, if we wanted to know exactly how many particles that this represents, well, that's also easy for us to do. So at a given pressure and a given temperature, which we can take from the data, from the graph, we can take that at a given temperature pressure, a given temperature, we can calculate the number of moles. And because we know that the temperature and pressure at a given, the number of moles at a given pressure and temperature, because N equals PV over RT, we can therefore calculate the number of moles. And we know that in 1 mole,